I would like to conclude this video series on the sign test by considering some of the characteristics of the test, both reasons to use it and cautions to consider. As you have seen as we went through the multiple use cases of the sign test, it is very versatile. The analysis is based on dichotomous data, and that fact alone makes it versatile because any kind of measurement or categorization can be turned into dichotomous data. There are many potential use cases, including the non-numerical comparison of paired participants, the detection of trend, the median of a single population, and the size of a treatment effect in a matched pair studies. Compared to other tests that may be considered as competitors to the sign test, there are minimal conditions for valid inference. Like all inferential methods, we need to begin with a random sample of participants. Nothing new or unique here. Of course, if you do not have a random sample, we are only estimating probabilities and we are only approximating inference back to a population that has characteristics that are similar to those of our sample. Another condition for valid inference that is not unique to the sign test, but again typical of many tests, and that is we need to have the independence of observations, or if we're working with paired data, the independence of the pairs. Now, if we want to make inferences about the location of a distribution, we have to have at least ordinal measurement of a continuous underlying construct. A test that might be compared to the sign test, the one-sample t-test, requires that we have quantitative measurement. Quantitative measurement will work here as well for the sign test, but the measurement has to be at least ordinal. The inferences about location are using the median rather than the mean. If we want to estimate the effectiveness of a treatment by using a matched pair design, we need to have the same population median for all of the participant pairs for inference about the median. As I discussed in a previous video when I presented this condition, it really is not a more strict condition because we commonly assume that we're drawing all the participants in our study from a single population. Instead, this particular condition allows us to draw from multiple populations as long as we have the same median of each population. The only time that would be realistic if we're drawing from multiple populations is if we want to test that there's some treatment effect versus no treatment effect. That is, we have a null hypothesis that the median of the different scores is 0. If someone wants to insist that you make inferences about the mean, you can do that with the sign test, but you have to add an additional condition, population symmetry. So population symmetry is not ordinarily a condition for valid inference, but if we add this condition, we can make inferences about the mean instead of the median because in symmetrical distribution, those two coincide. If you think about using a one-sample t-test to make inference about the mean, you also need population symmetry, but you actually have to take it a step further. You need to have a normal distribution, not just a symmetrical distribution. So you need a symmetrical distribution that has a particular form. Surprisingly enough for how simple and versatile the sign test is, it has some strong statistical properties. First, the test is unbiased. You may have heard about unbiased estimators before, but you may not have heard about an unbiased test. Many tests are, in fact, unbiased. In fact, all reasonable tests are unbiased, so this is not unique to the sign test. To be unbiased, it simply means that the probability of rejecting the null hypothesis when the alternative hypothesis is true is greater than when the null hypothesis is true. It should make sense to you that that's a reasonable thing to expect with a test. The reason that's really interesting with the sign test is because the parameter that we're interested in comes from a distribution that is unspecified. That's true with both the null and alternative hypothesis. We call those compound hypotheses. That is, the hypothesis does not completely specify the underlying distribution. If you were doing a t-test, you would have a normal distribution being specified, and you would specify what the mean is of that distribution. With the sign test, we have a compound null hypothesis because we don't specify anything about the underlying distribution, so it could be any distribution. Knowing that makes it actually quite interesting that the test is unbiased, that our probability of rejecting the null hypothesis is going to be higher under the alternative hypothesis than under the null, even though we don't know the distributions underlying either of those hypotheses. The sign test is consistent. Many good hypotheses tests are consistent. This simply means that as the sample size increases towards infinity, the power of rejecting the null hypothesis increases towards 1. So if we can obtain more and more and more observations, that's a good thing, as it should be. The sign test is also stable. The fact that it is stable means that it has good tolerance properties if we were to put an outlier in the sample, even if that outlier came from mismeasurement or a data entry error. By comparison, the one-sample t-test, which focuses on the mean, could be adversely and substantially affected by a single outlier. The sign test is relatively efficient and powerful with heavy-tailed distributions. We need to parse this statement a little bit. What do we mean by efficient? When we talk about the efficiency of the test, we're talking about the ability to reject the null hypothesis, and tests that can reject a null hypothesis with fewer observations are considered more efficient than ones that take more observations in order to reject a null hypothesis. When we say relatively efficient, that means, of course, that we're comparing the efficiency of this test to other tests. The sign test can be more efficient than many of its competitors when there are heavy-tailed distributions. That also needs some explanation. What do we mean by heavy-tailed? Typically, we think of the normal as the standard distribution. So heavy-tailed distributions are distributions in which we expect to have more observations in the tails than we would expect in the normal distribution. From a research standpoint, that means that as we get measures that tend to be more dichotomous, that is, tend towards the extremes, that the sign test becomes more efficient relative to its competitors. That should make some sense. It's almost like the distribution has a natural dichotomy. You might expect this, for instance, if you were gathering Likert data regarding a polarizing issue. And here might be the most surprising property of all when it comes to the sign test. At least this would surprise many researchers. It is the uniformly most powerful test of location with an arbitrary distribution. That means if we make no specification about the underlying distribution, almost as though the distribution itself was chosen at random, the sign test is the uniformly most powerful test of location. It is the most powerful thing we can do. If you have heard that the one-sample t-test is the most powerful test of location, you would be right as long as you have a specific kind of population distribution, namely a normal distribution. But if you know nothing of the distribution, the shape of the distribution can be considered arbitrary, then the sign test is going to be the most powerful test you can use. Now, with all those good characteristics in hand, you might suspect that there are some things we have to be aware of, and indeed there are. There are some cautions. The sign test can be relatively inefficient and less powerful with the normal distribution. We already knew it would be less powerful than the t-test with the normal distribution. But any light-tailed distribution, that is, anytime we have a distribution in which it's going to be difficult to dichotomize the data, the sign test can become very inefficient. We just saw that the sign test is uniformly most powerful for an arbitrary distribution, but now we're talking about specific shapes of distributions. While the sign test can exhibit good power with heavy-tailed distributions, by contrast, it can have rather weak power with light-tailed distributions. The power of the sign test can be highly variable as a function of the population distribution. We are going to see some statistical inferential methods later in this course in which, yes, the test might sometimes be less powerful, and yes, it might sometimes be more powerful. But one reassuring aspect of some of those tests is that even when the test becomes relatively less powerful, the power does not drop too far below that of competitive tests. The power of the sign test can be highly variable. Relative to its competitors, it can become much less powerful, and it can become much more powerful. If we always knew it was becoming much more powerful, that would be great. But the fact that it has high variability tells us we have to be cautious as we consider the sign test in view of the various shapes of population distributions. Now, a caution I'm going to give about the sign test that is not unique to the sign test, but is true of any test that requires independent observations, is that the lack of independence, that is, the observations being correlated, changes the error rate. One of the most common ways in which you can have correlation among observations is what we call serial correlation. That is, when the second observation is somehow related to the first, and the third somehow related to the second, and so forth. The error rate becomes conservative. That means that whatever nominal error rate we chose, we actually are going to be using a smaller type 1 error rate when there's negative serial correlation. That is, when the first observation and the second observation have a negative correlation, the second observation and the third have a negative correlation, and so on. It's going to be much more likely if we have serial correlation that it is positive. That is, when we make our second observation, it is somehow correlated to the first observation because we're not being careful about making independent observations. For example, if we were to make observations of individuals where it becomes more likely that the next individual is somehow related or knows the first individual, you could expect to see a positive serial correlation. And in that case, the error rate becomes what we call liberal. That means that we exceed the nominal type 1 error rate. And finally, throughout all the use cases that I showed you, I always talked about classifying an observation as a positive or negative. But what if we cannot do that? What if, for example, we have matched pairs and the member in the treatment and the control group score the same so that we have a different score of 0? In this case, we cannot do an exact test and we're going to have to resort to an approximation. There are 3 approximation methods that have been proposed. The one that is the most common is actually the one I like the least, and that is to drop observations that cannot be classified. The reason I like that the least is because if we are dropping zeros, we're in essence helping ourselves reject a null hypothesis, because we may be interested in determining if the treatment is effective, and I would say that a 0 says it is not effective. So you're actually dropping out data that favors the null hypothesis. Researchers should try to make rejection of the null hypothesis more difficult, not less difficult, in order to be able to validate their research studies. A second approximation is to consider unclassified observations as a minus for the one-sided test, that is, because if it's two-sided, a minus would in fact help out one or the other sides when we look at the alternative hypothesis. But for a one-sided test, the idea of considering, for example, a different score of 0 as a minus is something that I can embrace, because this is making it harder on us to reject the null hypothesis. Thus, a rejection of the null hypothesis is something we can be more confident about. If I know I'm doing an approximation, I would rather increase my confidence, not decrease it. And a final approximation method is to consider unclassified observations as half positive and half negative. Now, if you only have one of these unclassified observations, this isn't going to change the test at all. As you know, when we look at the binomial probability distribution table, we are going in increments of 1 when we consider the number of successes. So adding a half is not going to push us into the rejection region. On the other hand, if you have multiple unclassified observations, then 2 half plus signs make a whole plus sign. This method is really a compromise between the more liberal method of dropping observations that cannot be classified and the more conservative method of considering unclassified observations as a negative. In conclusion, what you have in the sign test is a very versatile test with good statistical properties, and as long as we take these cautions under consideration, meaning that we'll actually think about them when we conduct our research, the use of the sign test can be a powerful tool in your toolbox of inferential methods.